Determine the value of k that will make the function continuous at x equals 1. So here we have a piecewise defined function. The formula for the function can be one of two things, depending on whether the input is less than 1 or greater than or equal to 1. In such a case, there's often a jump discontinuity. But here, the formulas for our function involve a parameter k, which we can control. And if we choose the right value of k, then this function will be continuous at x equals 1. Notice that x equals 1 is where we have the change in the two formulas. Top formula if x is less than 1, bottom formula if x is greater than or equal to 1. Okay, now continuity. We say that f of x is continuous at x equals 1 if the limit as x approaches 1 of f of x equals f of 1. So we need for this to happen. And this limit is a two-sided limit. And if we have a two-sided limit that exists, then that means that the one-sided limits are equal. So it's probably best to look at this as two separate limits. The limit as x approaches 1 from the left is equal to the limit as x approaches 1 from the right, and then equal to the function value. So we should check three things. We should calculate all three of these things and see if they are all equal to each other. If they are, then the function is continuous. If they're not, then the function has a discontinuity. Now in our case, we're not just going to be asking, are they equal? We're actually going to set them equal because we're going to have a parameter at our disposal. So we're going to calculate these three things. They might not look the same, but if they have some unspecified parameter in them, then we can set up an equation and solve for the parameter. So let's look first at the limit as x approaches 1 from the left of f of x. Since x is approaching 1 from the left, x is less than 1, and if x is less than 1, we use the top formula. So the first order of business here was to figure out what formula should I plug in for f of x in this limit, because I have two choices. So we did that by noticing x going to 1 from the left, meaning that x is less than 1, and that tells us to use the top formula. So this limit is equal to the limit as x approaches 1 from the left of x squared minus k. And this is a plug-in limit. We could just plug in the number 1 for x. Be careful to leave k alone. It might be tempting to plug in the number for any variable that you see, but it's just x that's 1. The k will stay as it is. So this is going to be 1 squared, which is 1, minus k. Now let's try the other limit. The limit as x approaches 1 from the right of f of x. Again, our first order of business is to figure out which formula to use. And if x is going to 1 from the right, then that means that x is bigger than 1, and that falls in the bigger than or equal to 1 camp. And so we use the bottom formula. So our function f of x is replaced by kx minus 3. And x is approaching 1, so just plug in 1 for x, and we get k minus 3. And we'll also calculate f of 1. If x is 1, we're in the bottom camp again. Plug in 1, and you get k minus 3. So no matter what k is, the right side limit and the function value are equal. So this function will definitely always be right continuous. But we have to make the left side limit also match. So we just set up the equation 1 minus k is equal to k minus 3. And we solve for k. So here I think I'll add k to both sides and add 3 to both sides. So if we add 3 to both sides, this 1 will become a 4. And this 3 will disappear. Adding k to both sides, this k will disappear. And we'll get k plus k is 2k. So 2k equals 4, divide by 2, and we get k equals 2. So if k is 2, then this function will be continuous at x equals 1. If k is any other number, the function will be right continuous because the limit from the right does equal the function value, but the left side limit will be different and we'll have some jump discontinuity.